In this video, I'm going to work through a trigonometry level 3 example practice assessment. It will be the abstract kind. So this assessment has three sets of equations, set 1, set 2 and set 3. In each case we have to describe the relationship between f of x and g of x. So let's consider the first pair. We have this function sine 3x cosec x plus 1 and the one of 4 cos squared x. So the first thing we should do in all these sorts of problems is we should draw the graph of each function. So here I've got one of them in yellow and one of them in dashed black. As you can see, they appear to be the same. So I'm going to prove this by changing one of these equations, in this case f of x, into the other. And it's always important that you state how you're going to try and prove what it is that you're claiming about your graph. Now the reason I'm going to change f of x to g of x is because of this triple angle here, and it's always good to break down compound angles rather than trying to make them up. So here we've got our function f of x, and all I've done here is I've changed the sine 3x into sine 2x plus x and then expanded to write it like this. Cosec x is 1 over sine x, so I get this. The next thing I'm going to do is change the sine 2x into 2 sine x cos x, but I've got a cos x already, so it's cos squared x. And here I'm going to change the cos 2x into 2 cos squared x minus 1. And you'll see here that these sine x's cancel to leave me with 2 sine squared x plus, these are cancelled, 2 cos squared x minus 1 plus 1, and the minus 1 and the plus 1 cancel, and we can add these together to give us 4 cos squared x. So there we are, QED, Latin for in your face. Okay, now let's look at our next set. This is quite interesting because we've got these square roots going on, and these terms go from being positive to negative. You get some strange things going on because of course you can't square root the negative. Anyway, just like before, the first thing we do is we draw the graph of each, and this is why we get this odd thing going on. And we can see at no point does the g of x seem to intersect with f of x. So what I'm going to try and do is I'm going to try and solve this equation and see what happens. I'm going to basically rearrange this one and rearrange this one. So let's look at f of x first. So here we go. The first thing I'm going to change cos 2x to 2 cos squared x minus 1, and then we've got the plus 1. These cancel, and then we get this function here. These two will cancel. We're left with cos squared x square rooted, which will be cos x plus 1. Now let's look at this one going over here. We're going to change this one. So here, because we had a cos 2x, we automatically go to one of these equations. With this one here, whenever we've got a squared function, we're going to go to our identities for squareds, and we see that cos x squared plus 1 equals cot squared x. Now cot squared square rooted is just going to be cot x. Cot x is 1 over tan, so that makes it cos over sine. These sines are going to cancel, so we end up with cos x. And at no point can cos x plus 1 equal cos x. In fact, if they equaled each other and I subtracted one from the other, I'd end up with 1 equals 0, which is inconsistent with reality, which kind of shows that these things are inconsistent as well. Okay, now for the biggie. We've got our function f of x equals this lot here, and we've got this thing here that defines g of x. It's a sine function. It's got a maximum at pi 2 and a minimum at 2 pi minus 2. So I need to find out what this function is first, and we can use our knowledge of modelling to do this. So it's going to be in the form given there. A equals 2 because that's the amplitude, and really it's just half the difference between these, and the difference between those is 4. half of that is 2. D equals 0. D is just the average of the max and the min, or where the centre is. And then we've got a period is 2 pi, because from max to min is pi, we've got to double that, it's 2 pi. And remember, B is 2 pi over the period, so B equals 1. And then C is the negative of the distance to the max minus a quarter of a period. So C is minus pi over 4, which gives us g of x equals this function here. As always, we're going to plot those graphs, and here are our graphs here. The first thing I'm going to do is check, do I have a maximum for g of x at pi 2? So yeah, it looks like about 3.14, and at 2 pi, yeah, we do seem to have the minimum. Just got to always check those things. It's an easy check to do. And we can see that the graphs do certainly cross, and certainly they're not unique. So you could say these are consistent and unique. This graph is not the same as this one here. Well, in this case, if we get this thing, I'm going to prove this by actually solving the equations, letting one equal the other. So let's look at f of x first. Let's rewrite that in a more convenient form. So we've got a compound angle, we're going to expand, we're going to do the same here. The nice thing is that cos of pi over 4 is 1 over root 2. So pi times 1 over root 2 cancels, leave the sin x, and sine of pi over 4 is 1 over root 2 as well, so we just get cos x there. So okay, we've simplified that, so we're now going to do this one here by expanding, and here we get minus 2 cos x, and that's because cos of pi over 2 is 0, so this all goes. Sine over pi over 2 is 1, so we've got minus 2 cos x. So we're going to solve it. We're going to let those equal each other, and then we're going to take the cos x to the other side. Yeah, we've got sine x plus cos x equals minus 2 cos x. Take it to the other side, divide both sides by cos x, we get tan x equals minus 3. And then if we solve that in the range 0 to 2 pi, we get x equals 1.89. yeah, that looks about right, and x equals 5.05. that looks about right. Now look, when you're solving these problems, once you've got your graphs, tell them what you think's going on, tell them how you're going to go about doing it. So when it's this kind here, we're going to solve them. When it's the ones that don't ever meet, we're going to show that the solutions when you try to solve them are inconsistent. And when it's one on top of the other, you're going to say that there you're going to change one into the other using identities. At the end, say, look, yep, I've done the point here. One important thing, QED, it's nice to think it means in your face. It means that which is to be demonstrated, more importantly. Okay, staying in field with Winfield.